Hi everybody. Today we are going to see that PWM generation for buck and boost DC to DC converter for the application of power conversion. Basically, power electronic circuits which is used to convert one form of electrical energy into another form of electrical energy. It may be DC to DC or DC to AC or AC to AC or AC to DC. Okay. In our application, we are going to use that DC to DC converter. In the power electronic circuit, we are using that power semiconductor devices for the conversion application. To enable the power semiconductor devices, we have to give the gate pulses. In our application, our FPGA device will generate the PWM for the power semiconductor devices. So here we are using, instead of the meaning of the control circuit, the meaning is FPGA. For the buck converters, we can able to divide into two groups. One is buck converter. Basically, buck converter means that is the step down DC to DC converter. The meaning is, if you are giving the 10 volt input, the output may be the less than 10 volt. Based upon the on and off operation of the switches, we can able to get that variable DC output voltage, but it should be the less than the input voltage. This is the corresponding waveform and the corresponding formula. Voltage output, that is equal to alpha into VIN. Alpha, that is a duty cycle. It is the ratio of T on by total time T. That is the on duration divided by total time. It's the corresponding current waveform. During the on time it is increasing, during the off time it is decreasing. This is the diode current. Actually, diode, here is the diode is the freewheeling diode. It contains the two mode of operations. One is during the switching on period and another one is the switching off period. During the off period, freewheeling diode will come into play. Okay, this is the corresponding diode current. This is the boost converter circuit. It is the smallest little bit arrangement, changing the arrangement. So initially it will be starting with the inductor L. This is the primary device which is helping to get the boosted voltage. The device is connected here. Actually, during the turn on process, the circuit will be closed like this. During turn off period, the circuit will be closing via the diode and the load. The stored energy, the input as well as the stored energy will give the more output voltage across the load. This is a corresponding waveform during the turn on period and the turn off period, and this is the corresponding formula for output voltage. V output is equal to VIN divided by 1 minus alpha. Alpha, that is duty cycle, T on by total time T. See, this is our primary application. How we are going to use that FPGA device for generating the PWM for the DC to DC converter. It may be the buck converter or boost converter. Here there are 5 modules are there. One is a clock divider and another one, 2 clock dividers are using, as well as the push button, 7 segment, pulse counter and PWM generation. Actually, the meaning is what actually? See, actually DC to DC converter, the PWM have to be varied by using either by changing the frequency or else by changing the duty cycle. So how we are going to use that? By using these four push buttons, we are going to use that for increasing or decreasing. Okay. So frequency we may increase or decrease. Duty cycle we may increase or decrease for both the buck as well as the boost converters. So for that purpose, for any FPGA board, we may have certain peripherals, especially for the clock oscillator. The clock oscillator, it may be for the 50 megahertz or 100 megahertz or 200, or it may be the even gigahertz also. Because this clock oscillator will be used to design the any kind of sequential circuits. Okay, so for that purpose, we need that we have to take the clock input from the board. But for our case, for the sampling frequency of the push buttons, it is somewhat very less. That is, we are designing that it is 1 Hz. So just if you are pressing, it is increasing the frequency. Okay, so in such case, we need the module called clock divider. So this is overall modules. Okay, so here I can say the RTL schematic representation by using the ISE device, ISE software. So push button, clock divider for 7-segment display. This clock divider is for push button, and pulse counter, and the 7-segment display, and the final PWM generation. So the clock divider model, basically the clock divider that is used to convert 50 megahertz to 1 hertz. 50 megahertz, we can't be able to do that much sampling. So we need very less sampling for pressing the push button. Okay. So the output will be the clock output, we will get it. Okay. Accordingly, this is the simple flow chart for this. Okay. Whenever reaching this counter value, then it is changing the clock. It's changing its state. It may be from 0 to 1 and 1 to 0, like that. So this is the output of the clock output. And here this is the simulation output. Clock is the input and reset is the output. Okay, actually we are using that asynchronous high reset we are using. So here you can see that a reset will be 0 only. This is the clock output. Okay, 1 hertz clock we are generating here. Okay. And this is the device utilization. Why we need to think about the device utilization? Okay, say for example, any kind of product if you are taking, there are 3 kind of performance is important. One is speed, that is a processor speed. Second one, how much area it is utilizing. Third one, power utilization or else power dissipation. Okay, by the design. Okay, here our case, it is utilizing 21 slices. It is area. This is the area summary. Okay, 21 slices has been used for this particular design. This is the timing summary. It is achieving more than 150 megahertz. The meaning is what? We can able to the clock frequency up to 150 megahertz also. It will support, that design will support up to that level. Okay. And this for same kind of clock divider we are using for the 7-segment. One clock divider that is for the input. Another clock divider that is for the output, which we want to see the frequency, present frequency as well as the duty cycle both. Okay, for that purpose we need this clock divider. Okay, this is the corresponding flow chart. This is the corresponding flow chart. So the corresponding flow chart CO90264, the maximum value we are counting it, and it will be inverted, according to our requirement. Okay, this is the simulation output. The simulation output, you can see that same as it is high and low, it is happening. Okay, this is a device summary, the same summary we are getting. It's a timing summary, and this is the push button. So push button that is used to receive the input signal value from the push button. Whenever we are pushing the push button, it has to count. Okay, one time we are counting. Okay, so accordingly the 7-segment display also it will show the frequency. Okay, it may be 50 hertz or it may be 100 hertz or 1 hertz, whatever we want. Based upon the push button, the frequency can increase or decrease. This is the simulation output of the corresponding push buttons. See frequency counter, here it is increasing. Okay, here, so from 10 to 11, and it is increasing to another values also, it is increasing. So device utilization summary, it is 20 slices has been used, just 20 slices has been used. And a timing summary, it will go up to more than 200 megahertz it can able to achieve. Okay, see basically here it is showing that setup time and hold time requirement also it is showing, that we will see in the another video. Okay, so 7-segment display that is used to show to us either present frequency and present duty cycle, percentage of the duty cycle. Okay, 7-segment display basically working in the 7 segments A, B, C, D, E, F, G. It can display 0 to 9 as well as A to F. Okay, so one DP switch also used. Okay, see here duty cycle and frequency counter both are showing here. Okay, whatever we want. So selector, suppose if one switch we are using, it will show the either duty cycle or frequency. One switch, Just one switch we are using. I will show in the at the end of the video also. In the video I will show that. Okay. Right, device utilization. Total slices 266 slices has been used. Okay, this is the timing summary. For it can this is actually the device utilization summary up to 92 megahertz. This is actually the overall. No, sorry. Just this is for only the 7-segment display. Okay, timing summary up to 92 megahertz it can achieve. Then next very important thing is pulse counter is also very important. That is used to count the number of pulses. The input is 50 megahertz. Input is 50 megahertz clock signal. So that pulses it is used to count. Okay. Then this is the flowchart for that. So simulation output. So device utilization summary. Okay. For this up to 108 slices has been used. So it is working, it can work up to 139 megahertz. So the last module, that is a very important module, that is PWM generation. Okay, the duty cycle of the signal can be varied. Okay, so based upon the input of the duty cycle and pulse counter, the PWM will be generated. Okay, so flowchart for generating the PWM. Okay, so if the condition is true, then PWM will be 1, otherwise it is false. The input is coming from the pulse counter. The input is coming from the pulse counter as well as the frequency. Okay. Then the device utilization 126 slices has been used. The timing summary up to 108 megahertz has been utilized. This is the overall performance of the number of slices. How much slices has been used. It is optimized actually, so that the final output will be 128 slices has been used. So the timing summary 92 megahertz. And even you can find out the PWM buck converter, PWM for buck converter, PWM for boost converter. Actually, if we have the two different kind of circuits we have, we can able to generate, we can able to control both from the same FPGA device. So here it is showing buck converter, this is for buck converter, this is for boost converter, this is for PWM. This is important. And this is the video which we have in our lab. We have taken this. Okay, the push button also used, switches also used. There are two kind of mode we are doing that. One is frequency changing, another one duty cycle changing. Okay, this is the push button. We are pressing that. We are pressing the push buttons. Okay, it is increasing. In the 7-segment display, you can see that that is a frequency. That is a frequency. 25 hertz. We can increase that also. Yeah, now frequency is increasing. Even it works even 1 hertz to, even it works 1 hertz to 100 kilohertz. This operation can be, we can do that. Yeah, push button we are pressing and we will get that. So frequency almost 60% duty cycle now. 60% duty cycle now. Next operation we are going to fixing with the one particular frequency and we are going to change that duty cycle. See here. Now if you are pressing, if you are going to press that, see that how it is varying in the, yeah, see that the duty cycle is varying. Duty cycle is varying. Here actually P mode connector has been used to connect to the DSO. Okay, duty cycle beautifully we are varying. Okay, so in this way we can able to control that our devices. Okay, so if you have any kind of doubts or anything else is there, you can share your comments accordingly. I can also contact you. Our next video will be